This is homework 5, part B. We're going to be looking at a cooling tower and the multiple. We're going to derive the multiple different equations that can be used when looking at one of those, and then we will use Excel to see how those vary, how cooling towers vary when the height is changed, right? So first, we want to start by deriving our equations, right? So we have our cooling tower, right? Our water tower, right? And so that will be this here. One artist I know. So this is our tower, right? And we have our water coming in through the top here. This is TWN, right? That'll go down and then exit TW out, right? Different temperature. And then we have a T air in, right? And that's going to like combine a little bit with the water. And so we have our T air out, right? And because it combines with the water, we have to take into account not only our heat transfer, but also our mass transfer, right? So there, when you're looking at one of these, right, there are going to be, most of them will have what's called packing, right? Um, we'll have packing so that there's more surface area that the air can mix with the water, right? And I drew it as a kind of hash, but typically it'll be like a packed bed type situation where you have a lot of different spheres that are going in and things are coming through and going out, right? So when we're looking at a cooling tower, there's going to be 3 different things that we can look at, right? We can look at the change in temperature of the water with respect to Z. We can look at the change in temperature or the changing, sorry, the um, temperature of the air with respect to Z. And then we can look at the concentration of the water, right, with respect to Z. Right, these are the kind of the 3 things that we're going to look at, and we're going to drive these 3 equations. But first, something I had to mention is this packed bed type situation here has the units of meters squared per meter cubed, right? And that's to take into account um, the area over the total volume of the cooling tower. And so we'll have to use that in our derivations to take into account. But if we look at a smaller section of the cooling tower here, right? So we have this, right? And so it will kind of look like this with these little spheres scattered about, right? And we'll say that this is the positive Z direction, right? So our air is going with the positive Z direction, our water is going against it, right? So we have our air out, our water in, our air in, and our water out. Right, so this is kind of a zoomed in portion of the cooling tower over here, right? And one thing here, right? One thing that's going to be in our equations is the flow rate, right? So we'll have our flow rate of water, right? And so that is going to be kilograms per meter squared per second, right? And so when we're looking at a problem like this, you can do it either in terms of mass or moles, but it's important to be consistent throughout so that you can relate the equations together. And so here I'm doing it in terms of mass. And then for our air, right, we will have our flow in, which will be meters cubed per second times meters squared, right? And what you notice about this is this ends up being meters per second, right? So this is just our superficial velocity, right? And this will be used in a couple of the equations. to represent the flow rate of the air going in. Right. So the first thing we're going to look at is going to be the change in temperature of the water. Right. And so when we're looking at this, we have a couple of things that'll play into this, right? So we'll have our flow rate of our water, obviously. Then we'll have the heat capacity of our water because we're going to be looking at the change in temperature, right? And then we have to take into consideration the area, right? And then we can look at the change in our water, right? And so this is all going to equal, like that's what the rest of this is going to equal, right? And so when we look at that, we will have our heat and our mass transfer, right? And so if you remember the last video, we talked about heat and mass transfer, right? So our heat transfer, right? We have our area times our H times the change in temperature, right? But since we have this packed area, we have to multiply this by the packed area volume, right? And so we multiply it by our H. And then these two A's, right, that is essentially our volume, right? And so this is changing over Z, right? And this is dz, right? This distance along there, right? But then next we have to add our mass transfer, which is going to be our volume times our Kc, and then multiplied by the change in concentration, right? And this is going to be water minus air. And if you remember from the last video, right, to be able to relate these two equations together, we had to get them both into joules per second. And the way we did that was using the enthalpy of vaporization, right? And so one thing I'm going to do here, right, so this is basically our equation for dt dz. I'll solve for dt dz, but there are a couple of things I want to point out first. This concentration of water, if we use Antoine's equation, right, we know that it's going to be P saturation over our RTW, right? And then another thing that we're going to want to do is we're going to want everything in terms of heat transfer, right? So if we remember H equals rho Cp Kc, right? That's from our last video. That's the Lewis relation that we talked about. So Kc then equals H over rho Cp. We will also plug that in so that everything's in terms of heat transfer, right? So when we solve for dt dz, right, we then get A H TW minus TA over LCP, and this is Cp of the water, right? And then plus our lambda A, and then our Kc, which is then H over rho Cp of the air, and then multiplied by our LCP of the water, right? That's coming from over here. And we can cancel out the A, that's in all terms, and then multiplied, right, by our PSAT over RTW minus our CA, right? So I'm going to move this out of the way here, right? And so this is our equation for dTW. Next, what we'll look at is dC, right, our concentration of water, right? And so when we're looking at this, we know that it's going to be our G times our A times times our CH2O, right? Now I'm going to change this. So this is the concentration of the water vapor in the air, right? So I'm going to change this to C air. right? We're going to say it's air, right? And so with this, we're going to say that our G, right, our flow rate of air, and our A, right, our area, those are going to remain constant, right? So those will eventually come out of the derivative here. But right, this is all going to equal, right, our volume AA, right? Our packing times our overall area, multiplied by our mass diffusivity times the concentration of the water minus the concentration of the air, right? And then this is going to be changing, right? And so once again, we're going to plug in our H over rho CP for this KC, so everything's in terms of heat transfer, right? So when we solve for dC air over dZ, right, that will then equal AH over rho CPG, right? We get our G here. We can bring that out because it's constant, right? And our H over rho CP was put in for KC, and then we can multiply by our concentration of water minus the concentration of our air, right? So this is our equation for the change in water vapor in the air. And then lastly, what we'll look at is, right, our change in the temperature of the air over dZ, right? And so this one is a little bit more complicated, right? So what we have to take into consideration is the density times our velocity or our flow rate times our air, and then that all has to be that's all being multiplied by the CP of our air, um, multiplied by the temperature of our air, right? And then that is going to be added to the delta or the change or the enthalpy of vaporization over our density, right? Oh, that's a terrible row. Over our density multiplied by the concentration, right? And then that then equals, right? I'm going to bring it down here, right? So that'll equal our H, right? T air minus T water, dZ. And then also plus our KCA times the concentration over water minus the concentration over air, dZ. Now, if you look at this, right, this is right here. This is what we have. So we do not have to, or right, we can ignore this here because we would then be accounting for it twice, right? And so actually, when we're looking at this one, I'm going to rewrite this once again, and I'm going to plug in this P sat over RTW, right? That's from, right, we talked about that in the first equation that we derived. So that'll be in for that one. And so when we solve this equation here for dt air over dz, right, what we get is our AH over rho CPG times our change in water minus our change in air, dz, right? And this is our CP air, right? So those are our three equations for our cooling tower, right? We have our change in temperature of the air, our change in concentration of the water vapor in the air, and then we have the change in temperature of the water, right? And so now what I'll do is I'll put these into Excel, and we'll be able to look at how the height of the cooling tower affects the effectiveness and the efficiency. So that will be the next part of this video. Let me just switch over to the Excel. Okay, so this is the Excel portion of homework 5 part B, right? Right here I have part or the first part of this video on my iPad. I can't really get it to show, but I'll be looking down at that for the equations that we found in the last earlier in this video, right? So um here in this Excel, I've kind of put in some of the constants, right? Our water temperature going in is 323, our air temperature going in is 300, right? We have our Antoine coefficients for air. We have our gas constant. We have our step change, right? We have the relative humidity. We have the flow rate of water and the flow rate of air. Um, we have um, our packing um, size here. Um, and then we have our heat transfer coefficient, right? And so, uh, first thing we want to do here is we want to look at the saturation temperature going in, right? And so, what we'll do here is we'll do Antoine's equation, right? So equals, ooh, nope, well, that was bad. Equals parentheses 10 to the power of A air, and then um, minus parentheses B air divided by C air. And then we'll just say at 100, right, to get a basic temperature going. So plus 100. Ooh, um, and then um, we'll, and I need parentheses around this. Um, and I need another set of parentheses. And then what we have to do is multiply by um, our conversion factor, because this is in millimeters of mercury. We want it in Pascal, so it's 101,325 divided by 760. And then um, that gets us our pressure, right? And what I've done here is I've inserted these as formulas, right? Create from selection, left column, right? That's how I got this all to work out, right? Um, and so from here, what we want to do is we need a couple of things, right? We need the density of our air, right? So the way we do that is so that's it's our molar mass times our concentration. And we know that concentration is P over RT. Right? So we will start with our molar mass, right? So that will be 29 grams per mole for air, but we want it in kilograms. So it'll be 0.029 multiplied multiplied by our pressure, which will be 101, or which will be, yeah, 101,325, divided by our, I forgot an equal sign. Divided by our R, multiplied by our T air in, right? And so we'll get our density of air at 1.66, and that is um, yeah, that's our air. And then with that, we're able to find our Kc, right? We know that Kc equals H over rho Cp, right? And so we can do this where we get H, right, divided by um, rho air times the heat capacity of air, right? We have that down here, right? So we get 0.04, right? Um, Next, what we want to do is get our concentration of air, right? So this is going to be when it's completely saturated. So the relative humidity is 100%. And so we want to do here, we want to do our Antoine's equation, right? So we know concentration P over RT. Um, so we want to do our saturated pressure, right? So it's 10 times A air um, minus our B air divided by our C air plus, and we need to use the actual temperature of air. So I forgot an equal sign. And so it's going to be plus our T air in minus 273 because we need it in Celsius, right? And then we can close that, and then we need to multiply by our conversion, so 101,325 um, divided by 760, right? And then that whole thing, um, this whole thing will be divided by our R times our uh, T air in, right? And so we get 1.68 essentially. Um, And with that, what we can do is we can get our sea air in, right? The concentration of our air in, right? So all we're going to do here is multiply our 100% relative humidity concentration multiplied by um, our current relative humidity, right? And so we get 0.1679. Um, so that kind of takes care of most of our um, pre our preparation, right? The only thing we're missing here is our TW out. Now we don't know what our TW out is. So what we have to do is make a guess. Um, what we can assume is that there's no change in our temperature, or we can assume that our temperature of our water goes down to the temperature of our air coming in, and we know that's 303. So we can put our guess at 303. Um, from here, what we're going to do is we're going to start off like every other problem we've done, right? We're going to start with our counter, right? So we'll do 0 to 1,000, um, and we will go to fill columns 1,000, right? And then we will have our step times our counter, and then that can go all the way down, right? And so if we go down, we have a height of 5, right? So next, what we have the different things that are changing. So first, we have sea air, right? Because that's changing as you go, right? We have our temperature of our water, and then we have the temperature of our air, right? And then another thing that's changing as we go is our saturation pressure, right? So we have Psat, and then we know that the difference in concentration is changing. So we'll say that's C diff, right? Because as you change saturation pressure, you're going to change your concentration. And then from there, what we have changing um, is our equations, right? So um, we have our dT water, our DC air, and our DT, DT air, right? So those are the things that are changing in our problem. Um, when we look at this, right, our sea air, we have that concentration going in, right? C air in, our T water in, we know that, 323, or T air in, right, 303. Our saturation pressure at the start, that's going to be, um, oh, actually, this is not our water in, this is our gas, right? Because the water is coming in at opposite ends and we are starting. This is the bottom of our tower. Um, and this is the top of our tower, right? Um, so that would be our guess for our T water out. Then our P saturation, right? That's going to be another Antoine's equation, right? So 10 to the A air, um, right? A air, um, minus our B air, divided by our sea air plus our water minus 273, right? And then times our 101,325 divided by 760, right? Our conversion factor. And then what we have to do is, oh, actually, that's not right. There should be a parenthesis here and another parenthesis here. And then we get our saturation difference. Um, and then for our concentration, right, we have we have right our pressure divided by our R times our temperature, and then that whole thing is minus our our H here, right, our concentration air. Okay. And then what we have is the three equations that we found. If I can get my notes back up here. Right, so we have the three equations that we found, right? Our dT W dz, our dC air dz, and our dT air dz. Right, so those, I'm going to get those from the previous part of this video. So when I'm looking down, that's what I'm looking at. Right, so first our air, right, we have equals, um, right, A, right, that's our packing, multiplied by our H, multiplied by T water minus T air, right? And then that is divided by L, and then times CPW, right? And that needs to be another parenthesis. And then, let's see, plus parentheses our lambda uh, times our A times our H divided by, close that parenthesis, divided by parentheses our row air times our CP air or CPA times our L times our CPW, and then close that parenthesis, and then that's multiplied. Let's see, make sure my parentheses are correct. That's multiplied by the change in pressure. So times C diff. And Right, that's correct. Right, or 6.294, right? Um, and then next we're going to look at our changing the concentration of the air, the water vapor in the air rather. And we're going to leave this one in terms of mass, right? So our Kc. So we're going to go right A times Kc, right? That divided by G, right? And then that whole thing is multiplied by the concentration difference, right? C diff. Okay, I screwed something up. I missed the parentheses here. Okay. Oh, I forgot a period. Okay. And so that's our um value for our change in air. Next, we have our change in temperature of our air, very similar to our change in concentration of air, right? Just instead of the change multiplying by the change in concentration, right? So we're going to just take this, um, and we're going to put this here, but oh, okay. And then instead of multiplying by the concentration difference, we're multiplying by our change in temperature, right? So our TW minus our TA, right? And so that makes sense because they're the same right now. And then from here, what we're going to do is Euler's method to get uh, the change as it goes down, right? This is going to equal um, our previous plus the change in our step times the um, change, right? And we'll do that for each of these three, right? So it's our previous plus our change in step times the change in value. And then one more time, right? And then these can just come down, right? And so now we have two rows and we can just send this all the way down, right? And if we go all the way down to the bottom here, um, well, it appears I might have done something wrong. Hold on. Um, I just retried to send it all the way down and it worked this time. So what you can see here is right, we have our this is our right, we have tea water up here, right? And if we go all the way down, we notice that this is super high, right? Because as we come down, we start to see a drastic change, right? So it's probably about here-ish that it starts to change, right? But that's because you reach the saturation of 100%, right? And so you would need an extreme amount of heat um, to keep going, right? So if we take this value, right, this uh, 1003, I 1003, um, right? So this is that would be our T water in, right? This is a 1003, right? So our goal, right, is to get to 323. So what we want to do here is we want to take the sum squared, right? So this minus this squared. Oop. Uh, yeah, 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 I know. Right, and this number is humongous, right? And so what we want to do is we want to go to solver, right? So data solver, and we want to minimize this value by changing our guess for what the water temperature out is. And so if we go solve and let this go, right, we get a value that's very close to zero and very close to 323, right? Because it's not going to be perfect. But we see that now our temperature out of water is 299.8367, which gets us to 322.97, right? So that's going to round up to 323 in Excel Solver, right? So you're going to have a little bit of discrepancy there because of rounding, but that's essentially perfect. Um, and so that's kind of how it works with using Solver. Now, there's a couple of other things, right? One assumption we made was the relative humidity is 1. If that changed to 0.5, right, and we reran this solver, right, we let this go, right, that's a higher temperature. We see that that's much less efficient because as the um, relative humidity increases, right, it's harder and harder for um, there to be for the air and the water to not mix, right? And so it's going to be less efficient um, as a cooling tower, right? And same thing goes for our height. So like if we cut this height in half and resolve this, right, it becomes even less efficient because there's less time that water can cool as it goes out, right? And so those are kind of ways that you can see that the efficiency of a cooling tower is dependent on both the relative humidity and the height of the tower, right? The more humid it is, the less efficient it's going to be. The shorter your tower is, the less efficient it's going to be. So that's everything for homework 5 part B.